Taking dynamics this semester, I found myself interested in the phenomenon known as the Coriolis effect. Today, I will be taking my understanding of this concept a bit further in an analysis of the Coriolis effect with respect to storms.
So, watching the Weather Channel during a hurricane or nor'easter, you will notice that these massive storms spin over time as they make their way around. If you were to observe a storm in the northern hemisphere, it would spin counterclockwise. However, if you were observing the southern hemisphere, it would spin clockwise. And this rotation is all thanks to the Coriolis effect, a phenomenon that causes fluids like water and air to curve as they travel across Earth's surface.
First, let's take this volleyball to be Earth. The Earth spins from west to east along its axis. And the Earth is a sphere, which means that its widest point is around the equator. And our knowledge of dynamics will tell us that the points along the equator are actually spinning faster than those, say, on the north and south pole. So what does this mean? Let's go back to a classic example, a hang glider example. And for the purposes of this situation, this hang glider can travel for hundreds of miles. We're going to start our hang glider in Texas, and we're going to go directly north. You would think that if you went directly north, you'd end up somewhere in Nebraska. But that's actually not the case. Like I said earlier, the points that are closest to the equator are actually moving faster than those farther away. So Texas is actually moving faster than Nebraska, and the glider will follow suit. What we would actually see, and this is all thanks to the Coriolis effect, what we would actually notice is that this hang glider would end up somewhere in Delaware. It would veer to the right. This is the opposite in the southern hemisphere. In the southern hemisphere, let's say this is the equator. So this is now the southern hemisphere, this is the equator, and we are launching something. The observer is here. We are launching something. We would actually notice that it would veer to the left.
Now back to the hurricanes. The center of every hurricane is an area of very low pressure. As a result, the high pressure air surrounding the center or eye of a storm is constantly rushing toward the low pressure void in the middle. The Coriolis effect explains that the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls the air to the left, the opposite happens. Storms spin around the eye in a clockwise manner. Although we really didn't spend that much time on the Earth as a moving frame, or any time at all really on the Earth as a moving frame section in this course, I do find it very interesting to apply what I've learned in dynamics to something other than a mechanical system, which is why I picked this as my topic. And I think graduating as a mechanical engineer, it would be great to apply what I've known to not only mechanical systems but to things in nature such as hurricanes, etc., etc. What I hope to do in the written portion of this extra credit assignment is to analyze how storms move across Earth, and I'm going to be doing that by assuming that the storm is an object moving along Earth's surface. So I'm going to consider the storm to be an object, and hopefully this will be a good place to start.